Okay, can everyone hear me loud and clear? Anyone?
Yes, I can hear you.
Okay, thank you. Okay, let's wait for 2 more minutes, yeah? Before we start, 2 more minutes. Okay, I think we can start now. I think we can start now. So I'm going to stop sharing the QR code. Okay. All right. So I think I mentioned in the Telegram group, yeah, this I think this noon that we are going to talk about CST. Okay. So far, I think we have talked about beam, solving beam element problem. We talk about solving heat transfer problem. I think for the case of composite wall. And then today is another uh, topic, which is CST problem, solving CST uh, element problem. So basically, by this, you should be you are prepared to take the test because these are the three topics which will be on test two. So these are the topics that will be on test two. All right. So and then I think before test two, I hope everyone remembers. Test two is on the 29th. 29th of June. Today is what 8. Yeah. Today is 8. So we still have what 21 days. About 21 days. Still a lot of times, but I'm not going to uh, not going to stop, but you must remember we also have one more topic where we have not discussed, which is thin fin, heat transfer in thin fin. That one has not been discussed yet. Okay, so by the way, before test two, I'll give you another review question based on past year test two problems. Okay. So I think each question is allocated about 45 minutes, and you should time yourself. You should time yourself not to exceed 45 minutes. Yeah. All right. So for today's discussion, what we are going to do is to do this one. Let me share the display first. Okay. Today what we are going to do is to do this question. This is from past year. Again, past semesters. I don't remember which semester, but this was my question. This was my question. Remember that time is 45 minutes to answer. And I think during that days, you were given 15 minutes to submit. I think this is more than enough. Actually, five minutes is good enough to submit, actually. So you have an extra time here, kat sini. So these are the basically an overview what kind of question that you can expect for CST or CST. All right, so just like I told you, this is from past semesters. I don't know which semester, but this is an old one. All right, so in this question, it says here figure Q2, question number 2, shows a support plate with thickness of 20 mm. So this is the support plate. This is a support plate. This is just like trapezoidal in shape. Okay, and its other relevant dimensions. So the thickness is 20 mm, and if you look at the rest, the dimension are all in meters. 1 meter, 1 meter, 1 meter, 1 meter. And then we have 10 kilonewton and 10 kilonewton point load at this point here. And then we also have a uniform distributed load of 2 kilonewton per meter square here. Okay, and then all these are supported by pin joint at node 1, node 3, and node number 5. Okay, so the plate is supported by fixed joints at 3 nodal locations at the top edge and are loaded with 10 kilonewton concentrated load and 2 kilonewton per meter square uniformly distributed load at the bottom center and bottom edge respectively. So bottom center is the concentrated load, point load, and then the uniform load is here at the bottom edge. This is at the bottom center. Okay, respective ratio. The Young's modulus is 10 gigapascal, and the Poisson ratio is 0.3 for the plate. Node 1 is located at 0.00. So basically, this is the origin. This is the origin. So the coordinate is 0 and 0. All right, so that is the situation. That is the situation. Yeah. Okay, so next one is let's read the question. Let's read the question. State the type of problem relevant to this case for the purpose of determining the correct stiffness matrix and parameter to be used. Okay, so if you take a look at this figure, you notice that this is our first 2D element, right? Our first 2D element. So 2D element has an area, okay, has an area. And of course, when you have an area, you also have the, since you have the thickness, you have thickness of 20 mm, then what you have is the volume of the plate. Okay, so I don't know if you remember during watching my lecture, okay, my video lecture, but there are two types of problem in CST. Okay, for example, if you take a look at the formula sheet here, okay, note that there are two types. First, let me change to red color. First, plane stress, and the other one is plane strain. Plane stress and plane strain. So what's the difference there? What's the difference? Okay, So I hope you know what are the difference. Okay, I know what are the differences between plain stress and plain strain. It's in my video, also in the textbook. So you have it or not in UBD, I think you should be honest enough to know if you watch or not watch my video. So in this case, what kind of thing the question asks for? Okay, state the type of problem relevant to this case. We know that this is a CST problem, but is it plain stress or is it plain strain? Okay, plain stress or plain stress? Stress. So which one? Okay, so these are the idealization. Instead of using 3D, we use either plain stress or plain strain to avoid the complication of using a 3D element. Okay, if you want, you can also use 3D element here, but we simplify this problem. It becomes a 2D problem, which is in this case CST. But you need to understand, are we going to use plain stress or plain strain? Okay, so that's the thing. Because the formula are different. From plain stress is this, for plain strain is this. Okay, and this thing too, they are different. So which means if you use the wrong idealization, your K matrix here, this is your K matrix, okay, for CST, note that there are D here, D11, D21, D11, D21, D11, D21. So if you use the wrong D, the wrong idealization, then your stiffness metric will be wrong. So this is the issue. So please, before you do, make sure you understand the difference between plain stress and plain strain. Okay, so we are going to use this formula. We are not going to use, this is the simplified version. But if you look at your derivation for your K matrix, it is not easy to calculate, right? So in this test, we already given you the CST. Okay, we have given you the CST formula. So you can straight away use it. You can straight away use this formula, provided that you know what is D11, Y23, DP3, X32, and so on. Okay, so now let's look at this. So CST, which one? Plain stress or plain strain? So that is the problem here. Okay, plain. It's not allowing me to write. Okay, so I think we have to wait for a little bit because my PC is running. It's running out of memory, I guess. Okay, let's see. Oh no, my memory is still good. Okay. Okay, the PDF reader is using a lot of memory. Okay, so that's one issue. That's one issue. So before you do anything, because this is part A, when you got part A wrong, and that's it, the rest basically wrong. This is very important. So plain stress or let me change that. Okay. So that's the first one because we need to identify the problem. So we use the correct formula for our problem. That's one thing. The other thing is taking advantage of the plate geometry and its loading symmetry. Okay. Model this problem using two triangular elements. Okay, sketch the model and label clearly all relevant nodes, element, and degrees of freedom. So this has something to do with your project. This has something to do with project because if you look at this, not only the shape of, or not only the geometry of the plate is symmetric, but also the loading. So in this case, we can do half of half model. We can model this just using half model, not full model. And it says here, because it says here taking advantage, so which means the problems want you to do this using this symmetrical way. Okay, and two CST elements, two triangular elements. Sketch the model, which is in this case half model, and the label clearly all relevant nodes, elements, and degrees of freedom. Obtain the reduced stiffness matrix. Okay, normally we reduce it during our assembly, but now, in this case, because CST, it has 2 degrees of freedom per node, and CST has 3 nodes per element, so we have a 6 by 6 stiffness matrix, element stiffness matrix. So it is good if we can reduce at early stage so that our assembly will become easier. And again, assemble the reduced global stiffness matrix. Okay, calculate the load at relevant nodes and assemble the global force vector. So once we get the global stiffness matrix and we get the global force vector, okay, we can set up the SLE and then solve for the unknown displacement. So this the first I think the first 6 steps, the first 6 questions are basically helping you to set up your problem, to set up your problem. So this is the idea. So this is test 2. Test 2 still we give you guidance, but if the same problem is for final exam, it will not have all this part A, part B, part C, part D, and so on. It will be much simpler because we are going to test you on your understanding of how to set up the SLE and solve the SLE. Okay, that is the idea for test for final exam. For final exam. All right. So once we get that, we can get the strain and the stress standard. Because once we get the displacement, we can use our solid mechanics relationship between stress, between displacement and strain and stress. So that's the idea. So the important step is up to step F. Okay, so that's the idea. So now my question is, how do we start here? How do we start? Okay, so look at this. It says here, state the CST type of problem here. So that's the first thing, because if you look at the formulation, you need to use D, this letter D and D. So now, which is which? Which is which? Okay, I hope you have watched my video. I hope you have read the textbook in such a way that you know that this is a plane stress ke plane strain problem. Okay, so since nobody is willing to answer, I just tell you I'm using plane stress. But I don't know why. I think you should know why I'm using plane stress. All right, so in this case, part A, it is a plane stress problem. Okay, why? I think you should know why. All right, so that's the idea. So, and then I think the next question was asking us to, okay, so state the type of problem relevant to this case for the purpose of determining the correct stiffness metric and parameter to be used. So what we need to do is to say it's a plane stress problem because so there are two answers there. First, either plane stress or plane strain, and then the reason why you choose plane stress. All right, so that's the first one. I think I've received a question. I don't remember from which class. Is it from my, I don't remember, is it numeric class or FE class? But student keep asking me for answers. So, but I will not give you the answer straight away. What I want you to do is to find the answer. So I guide you. I will guide you to get the correct answer because this is a learning process. If I give you straight away the answer, the thing becomes spoon feeding process. This is not what I want to do. So I'll tell you what to do, or I'll guide you for the answer. I will not give you the answer straight away. So the same case here, because nobody answers my question. So I want you to find it on your own. I have given you the sources, my lecture video, I think the slides, and of course the textbook. Okay, of course the textbook. Ada semua tu benda tu. Right, the next thing to do is okay, the next thing to do is the next question is this one. Part B, taking advantage of the fluid geometry and its loading symmetry, model this problem using two triangular elements. Okay, sketch the model and label clearly are relevant nodes, element, and degrees of freedom. Okay, so if you look at this question here, okay, of course, you can do this straight away. You can do this straight away. But if you look at the node points, okay, there okay, before that, let's do this. Let's make it to let's split these two CST, triangular division or triangular shape. Okay, we know that the easiest shape will be like this and this. So there are 1, 2, 3, 4, 5. There are 5 degrees of freedom. And 5 degrees of freedom, okay, there are, 5 nodes, and there are 2 degrees of freedom for each node. In this case, this is Q1, and this is Q2, for example. So we have 2, 4, 6, 8, and 10. So we have 10 degrees of freedom. Okay. Now, how many boundary conditions do we have here? What is the boundary condition at node 1? Anyone? Wow. I don't think we should have class this afternoon. Ramai yang senyap je, saya tak tahu kamu tidur ke, kamu dengar ke, apa ni. Hello? Hello? Anyone home? Hello? So what's the answer here? What's the boundary condition at that point? At point 0, 0, at node number 1. What is the boundary condition there? What kind of join is that? It's a pin join, right? So what's the boundary condition for pin join?
0, doctor.
What's that?
0.
0. What is 0?
For Q1 and Q2.
Okay, because it is spin, right? It is spin. It cannot move either in the x direction or in the y direction because it is fixed. It is joined there. It's a pin there. It's a pin there, so it cannot move. So this is 0 and 0, right? How about this? We know there's Q5 and Q6. So what's the boundary condition here?
Same, doctor.
The same thing. Okay, saya minta tolong lah, please lah, orang kata interaktif lah sikit dalam kelas ni. Because the problem here is I cannot see you. You turn off your cameras. I don't know if you are in the front of screen or not. And then if you just passive, you learn nothing actually. Okay, you do not learn anything by listening. You might get fallen asleep. Okay, so please be active. Okay. Now, how about this one? Q9 and Q10.
Same also.
Same. Okay. Now, how about Q3 and Q4? Is there any boundary condition there? Is it fixed?
No, doctor.
So, Q3 and Q4, basically at node number 2, it can move horizontally in the X direction or in the Y direction, horizontally or vertically. So, Q3 and Q4 is our unknown DOF. How about Q7 and Q8?
Also same. No
Same thing,
boundaries.
right? Same thing. So if you look at this overview, you can see that there are 10 degrees of freedom, okay? But we have 6 boundary conditions. So how many are unknown DOF? There are 4 unknown DOF. So we expect when we assemble the global SLE, okay, the total number of unknown is 4. Okay, because we have seen this before. Okay, we have seen this. We have to take a look at everything here, and we notice that we are left with only 4 unknowns, which is in this case Q3, Q4, Q7, and Q8. So this is a 4x4 matrix that we need to solve. But this is not taking the advantage of symmetry. So it says here, okay, it says here that taking advantage of the plate geometry and its loading symmetry. So we need to take into account of this. So it becomes easier. So building a 10 by 10 matrix is not easy. Why? If you take a look at the formula, this is only for one element. Yeah? This formula is only for one element. Yeah? And you spend a lot of time in the test doing the calculation, which is very time consuming. So the strategy here is to make it as short as possible, as short as possible. So I'll show you how to do this. I'll show you how to do this. But janganlah diam diri je. Because I believe this is when you listen only, it'll be a passive learning process. Bila passive ni banyak benda tak menjadi lah. Okay. Alright, so the next thing is this. So okay, now we know that it can be the symmetric shape and the symmetric loading can be taking advantage of. So macam mana kita nak buat ni? We only use half a model. Remember, in your project, you are using quarter model, kan? Quarter model, because you cut it half in the x-axis, you cut it half in the y-axis. Okay, because there are 2 axes of symmetric for your project. Okay, for your project, but for this case, it has only one symmetric axis, which is it vertical or is it horizontal?
Vertical.
Vertical, okay. Kesian Zafira ni, orang lain tak ada ke? Sorry Zafira, it's just a joke. Alright, so saya tak tahu lah orang lain ni ada ke tak ada. But please participate. Please participate. Alright, so in this case, what we want to do is we know there's a axis of symmetric here. So the axis is a vertical axis. So let's see if you can do it this way. Okay, let's see if my symmetrical axis, can I do it this way? Okay, let me make this smaller. So can I use it this way? Is this my symmetrical axis for the plate? What do you think? What do you think?
I think fine.
Okay, this is good, right? Because if you take a mirror and put it in the center on the line, you can see it's the same shape, right? So that's the axis of symmetry for this project. I mean, sorry, for this problem. Okay, for this problem. So now we know that we only need to study half of the plate, which is this one. But remember, in the project, it says that you can make it symmetric, but you need to have the appropriate boundary conditions. Okay, before this, we have 10 degrees of freedom, we have 6 boundary conditions, and then we have 4 unknown degrees of freedom, right? But we do not change anything. We do not change the boundary condition. So what are the boundary conditions here when we cut it into 2? What are the boundary conditions here? Note that this one still the same, pin joint, right? So we know that that condition is Q1 and Q2 will still be 0. And at node number 3, this is also pin joint. Now, what about this one here? How about this point here? How about this point here? Node number 2 has no boundary condition, right? So this is node 1, node 2, node 3, and let me renumber this as new node number 4. Okay, so now what are the boundary conditions here? When we cut it into 2, okay, when we cut it into 2, we know that we need to enforce a boundary condition at this edge here. This edge. So we need to put a boundary conditions here. So what are the boundary conditions then? What are the boundary conditions over at that edge there?
No boundary condition.
This is where it's become critical. This is part of learning process. Okay, so remember in your project, when you cut it into 4, you cut it at the horizontal symmetrical axis and vertical symmetrical axis. You should put an appropriate boundary condition. So in this case, if you look at the full model, what will happen? What will happen to this shape when we put the load here? So basically, we can see something like this is the unloaded. This is the unloaded position. But when we load it, what will happen is that it should look something uh, something like this, because the plate deform, the plate deform because of the loading here and the loading here, the concentrated load here. Okay, the concentrated load there. Okay, so we see that it will look something like it will become slightly thinner, and then it will something like this. Okay, you can do this on using ANSYS and you can see the shape. You can see the shape. And note that again, the deformation will be symmetrical. Will be symmetrical. And note that this center, okay, will expand. Will expand from this location to this new location here. Okay, so it will extend it because of the deformation. Because of the deformation. Okay, it will extend it from this location. This is the initial location without the load, and then extended to this load, which means we can see that the center line here move along the vertical axis. So because of that, we can model this as roller support. Okay, as roller support, because this edge is moving along the vertical symmetrical axis because of this. All right, so now we have a new boundary condition for our model here. So we know that okay, before that, let's look at the second question. It asks for Okay, model this problem using two triangular elements. So, okay, so how do we divide this to two triangular elements? Can we use it this way? These are two triangular elements, right? 1 and 2. Or should we use it this way? This way. This is 1, this is 2. So which one do you think is a better model here?
Number 2, Doctor.
This one or this one? Zafira?
Maybe number 2, the one
This one.
on the right. Yeah.
Okay. So why? Why? Right. So from the look at it, you can see that, oh, okay, the second one is much better. But there are mathematical reasoning behind it. Yeah? The mathematical reasoning behind it. First of all, note that the angle here is obtuse. Okay, which means it is just, this is mathematical thing saying that the angle is more than 90 degrees. Okay, that's it. And, okay, there's one angle which is more than 90 degrees. Certain finite element software, because of the formulation, when you have an obtuse angle in your element, what will happen is that the result will become not as accurate as you want. So avoid anything that is more than 90 degrees. In this case, you look at this is 90 degrees, this is less than 90 degrees, this is of course less and less and less. Okay, but this one, if you look at this one, this is 90, which is okay. This is less and less, less, but this is more. So this is a better option. This one is a better option. The second one is a better option. Okay, note that uh, like abacus. I don't know if ANSYS can do this, but abacus, it will check, it will comment on your elements. It will comment and say, okay, this is not good because of the angle is more than 90 degrees. So what we want to do is to find anything, okay, especially 2D elements, what we call with acute angle, which is acute is just another fancy word for less than 90 degrees or equal to 90 degrees. So this is what it meant by acute and obtuse. Acute angle, obtuse angle. That's it. So we are going to use this one, the one with the acute angle. The one with the acute angle. All right, so this is how we choose. This is how we choose, because if you look at previous year's question, it will ask you to find the best configuration in such a way that it will give you the most accurate result. So one way to get most accurate result is the angle, to look at the angle. So in this case, looking at the angle, for the second one, all the angles are maximum 90 degrees. Maximum 90 degrees. But for the first one, there's one angle at node 2, which is more than 90 degrees. So this is how we avoid certain issues. Certain issues. Okay, so now we can go to the next one. Okay, so sketch the model and clearly label all relevant nodes, element, and degrees of freedom. So let's do this. Okay, so part B. So what we'll do is we'll do it this way. Okay, we'll do it this way, and note that I'll be using, this is node 1, no change. Still the same original node numbering. And this is 4. Okay, so this be your, if we draw it asks for, okay, sketch the model and label clearly all relevant nodes, element, and degrees of freedom. So in this case, this is node number element number 1. This is element number 2. So we have two CST elements, and then this is Q1 and Q2. So Q1 is 0, Q2 is 0. How about Q3 and Q4? Oh, sorry, not Q3 and Q4. This is node 3, so we take 5 and 6. So this is again 0 and 0 because at node 3, it is fixed. It is fixed by pin join. And this is Q3 and Q4. Q3 and Q4 is our unknown DOF. And we have Q7 and Q8. So note that for Q7, we have a boundary condition. What is the boundary condition for Q7?
Roller.
Okay, roller. So at this point, it has a roller. Okay, it's supported by roller, but can it move to the right-hand side? Can it move horizontally?
No.
No. So in this case, we know that this is 0. How about Q8? How about Q8? Can this point move upward and downward?
Yes.
Yes. So in this case, Q8 is another one of our unknown degrees of freedom. Okay, so this is the unknown degrees of freedom. How about other things? How about the other things? Other thing we can see that. Okay, so it's stuck now. Okay, note, how about the loads there? How about the loads? Okay, we know that at this point we have concentrated load, right? We have concentrated load. Okay, so we have okay, tunggu sekejap I think what is wrong here? My PDF reader is eating up a lot of my memory here. So maybe we can turn off one of this. Okay, still hanging. It's frozen. Okay. So note that in this case that it can move upward and downward. So okay. So Q8. And note that here we have our loading. We have our loading here. So we have distributed load here for the first, this one here. We have our distributed load at this point here. So that's one concentrated load. So definitely we have F8. We have F8. Okay. I think something wrong with my PDF reader. I think I need to either install it or find a better PDF reader. It's eating up a lot of memories. Okay, let's wait for a few more minutes. Okay, so now we have the degrees of freedom. We're also trying to put on the loading for that point. So we have, in this case, F8. F8. Okay, so it's not moving. I think what we'll do here is just maybe kill this PDF reader. Okay, so I've killed it. So let me restart my PDF reader again. Okay, so let's share that back. Okay, so now you got my back. So you got this back. So this is our F8. Of course, there's F8. Okay, and there should be also load at node number 2, which is F4. F4. Because of this distributed load and concentrated load. Okay, so that's the model. That's the model for our half model. For our half model. So we know that now. Okay, our boundary conditions are Q1 equal to Q2 equal to Q5 equal to Q6 equal to Q7 equal to 0. And our unknown DOF, note that we have how many nodes here? 1, 2, 3, 4 nodes. 4 nodes means we have 8 degrees of freedom. 8 degrees of freedom. And so DOF, we have 8. And unknown DOF will be 8 minus 1, 2, 3, 4, 5. So 3 degrees of freedom. In this case, what are the 3 degrees of freedom that we are interested in? We are interested in Q3, Q4, and Q8. So we already know that the final SLE will be a 3 by 3 matrix. Will be a 3 by 3 matrix. Okay, so if you get more than 3, I think you know that something is wrong. Something is wrong somewhere. You better go and double check your model, okay, or your calculation. So it should be 3 by 3 matrix. So at least now you know the solution to this problem. Okay, at least the picture or the overview. All right, so in this case, what we have here, I also need to do this my element connectivity table. Element connectivity table. Okay, so for element 1 and element 2, you know that for our CST, there are 1 local node, there are 2 local node, there are 3 local node. And for element 1, local node 1 is this, local node 2 is this, local node 3 is this. So this is the same, 1, 2, 3. And for element number 2, local node 1, to me is this one, which is global node number 3, 2, and 4. Okay, so this is very critical, this element connectivity table. Element connectivity table. Now let's do the next one. It asks for, C is asking for, okay, obtain the reduced stiffness matrix for each of the element. For each of the element. So before we can do that, okay, remember part A here. Okay, remember part A. So question part C is the reduce element stiffness matrix. Okay, so this is where we need to use our formula. We need to use our formula. So the formula is this. Okay, so note this is the formula. So note that this is for DOF1 local node, local, because this is element level and not the global level. 2, 3, 4, 5, and 6. Okay, 1, 2, 3, 4, 5, 6. Because for CST, we know that we have node 1. Node 1 we have Q1, Q2. Note that I'm using small letter Q here, small letter Q here, because of element level and not global level. So this is local node 1, local node 2, and local node 3. So this is our Q3, Q4, Q5, and Q6. So this corresponds to all the degrees of freedom. So 1, 2, 3, 4, 5, and 6. Okay, so this is very important. So before we can use this formula, I mean this formula sheet, you note that we need to have D11, D33, and so on. So D depends on what kind of problem you are dealing with. Are you dealing with plane stress or are you dealing with plane strength? In my case, I say this is a plane stress problem. Okay, so I can calculate my D11, which is equal to D22, and so on. So let's calculate that one. So I said this is my plane stress problem. So plane stress problem. So we know that D11 equal to D22 equal to E over 1 over mu square. That one is from the formula sheet. This one. So I just basically use the formula, and we know that our E is 10 gigapascal. Our mu is 0.3, and our T, thickness of the plate, is 20 millimeter. 20 millimeter. Note again, I convert everything to basic unit. To basic unit. So if you do the calculation correctly, this should be this value, and D11, D12 equal to D21, because this is symmetric. Basically, this is symmetric. This is just mu D1 minus mu square, which is 3.2967 times 10 to the power of 9. And lastly, D33. D33 is just E over 2, 1 plus mu, which you calculate should be 3.8462 times 10 to the power of 9. Okay, so this is the common value that we need to use, because in the formula we need to use all this D11, D22, D12, D21, and so on. Now it's frozen again. Okay, so this is very frustrating. Well, if I take a look at this is not as critical. It's only using 1%, only 5% of the memory, but still I'm having problem here. Okay, so note that because of the formula requires the use of D, so we have to use that. And now let's look at second one. So let's look at element number 1. So we know that element number 1 is this. Okay, this is element number 1, and element number 1 is this. So, sorry, terbalik. Element number 1. Okay, so this is element number 1. This is element number 1. So, let me reopen. Okay, so this is element number 1. So 1, 3, 2. Okay, when you do this CST, there are things that you need to be very careful about. For example, for element number 1, so this is element number 1. We take note that this is node 1 local because of this, because of this element connectivity table. So this is node number 2, and this is node number 3. Note I'm using 1 hat, 2 hat, 3 hat. So this is local. This is local. So the coordinate is 0 and 0. And then this is, of course, you can calculate this. 0.5 minus 1. And note number 3 is 1 and 0. I think if you look at the question paper, you can straight away find the coordinates. So the coordinates here, let me rewrite the coordinates here. X1 equal to 0, y1 equal to 0, x2 equal to 0.5, and y2 equal to minus 1, x3 equal to 1, and y3 equal to 0. Okay, so this is the coordinates. These are the important information. The other important information for you is to note that the numbering scheme, the numbering of the node scheme. So in this case, this is node number 1, this is node number 2, this is node number 3, and it must go counterclockwise. It must go counterclockwise. This is in your textbook. Okay, this is in your textbook. I think I don't recall if I mentioned this in the video, but let me remind you again, the numbering system should be in counterclockwise system. So 1, 2, and 3. Okay, so what else do we need in the formula? What else do we need in the formula? Okay, so we also need this thing here. Okay, so we get calculated D11 and so on, and we also need we need y23, x32, and a lot of other things here. 32, 23, 32. What are all these numbers? And also we need this. We need this because we need J here, because we need to calculate the area of the CST. Okay, the area of the CST. So we need to find what is J here. And for J, it requires x13, x23, y13, and y23. I think I mentioned this in my video, but just in case you haven't watched my video, let's talk about this. So in our case, we need to find what is x13. X13 is basically telling us, it is a notation that saying that this is x1 minus x3, a short form of the long notation. So x13 means x1 minus x3, and in this case, x1 minus x3 is minus 1. X23 is just x2 minus x3, which is x2 minus x3 is minus 0.5, and y13 is y1 minus y3, which is y1 minus y3, 0 minus 0 is 0, and then y23 is just minus 1, y2 minus y3, minus 1 minus 0, which is minus 1. So our j, okay, our j, according to the formula given in the formula sheet, is just equal to, okay, x13, x13, y13, x23, y23, x13, y13, x23, y23. So this is just filling the blanks. So this is just minus 1, minus 0.5, and then 0, minus 1. So determinant of j is just It's just this time this minus this time this, so equal to 1. And the area is half of determinant J, right? Half of determinant J. So it is just equal to 0.5. Okay, equal to 0.5. So the formula is not. Okay, let's close this. Reopen the formula. Okay, so you should have your formula sheet with you. This is tiring. Sheet. It's not showing the formula sheet. So what I'll do here is maybe I take a look at my just take a look at my solution here. So the area is 0.5, and then we also need T over 4A, which is part of the element stiffness matrix. So this is 20 times 10 to the minus 3 divided by 4 times 0.5, which is 1 times 10 to the minus 2. Okay, please take a look at the formula sheet. I just cannot open my formula sheet here because of this issue. So we are complete with our data for element number 1. Okay, so what we need to do is to find what is our K of element number 1. So wow. We need to take a look at the formula. So look at element number 1. Look at element number 1. We know how many degrees of freedom are there. How many degrees of unknown degrees of freedom in this problem. So we know that Q1, Q2 is 0 here. We know Q3 and Q5 and Q6 is 0 over here, but we only have Q3 and Q4. So in this case, it's a 2 by 2 matrix for element number 1. Okay, I'm not satisfied. I think I need to show you. I need to show you this formula. Hopefully I can open this. It's not showing the formula. I think I have to close this and maybe open it. Okay. Okay. All right. So note, this is part of the calculation. T over 4A. So I have calculated this thing. T over 4A. Okay. And okay, so in this case, we know that for our element number 1, we know that let's change color so you can see that the degrees of freedom, what degrees of freedom we are interested in. So our Q1, Q2 is 0. Note that again, I'm using small q here. Q5 and Q6 equal to 0. But what we have is only Q3 and Q4. So do you think this is the correct degrees of freedom for element number 1? I hope you can see, this is for element number 1, for element number 1, right? So now this is T over 4A, which is just 1 times 10 to the minus 2. Okay, 10 to the minus 2. And we have Q1, Q2, Q3, Q4, Q5, and Q6. Okay, so this is again Q1, Q2, Q3, Q4, Q5, and Q6. But note that we are not interested in Q1 and Q2 because there are zeros. Okay, there are zeros. There's no displacement at all because it is fixed. So we are not interested in this column and this column. Okay, note in this question, it is not asking you to find the reaction, right? So when reaction is not needed, we can also cancel out this. Okay. What are the rest of the boundary conditions? So we know that Q5 and Q6 are also not needed. So Q5 and Q6 are not needed. And because of that, and again, because there's no question asking about the reaction, so we can just simply ignore this. So what we have left is only Q3 and Q4, which in this case, let me write it as A, B, C, and D. These are the four elements. These are the four elements of the matrix that we want. So what is A, what is B, what is, sorry, I think I'll change the numbering here. So A, B, C, D, C, D. Note that C and D are sometimes symmetrical. Okay, so commonly, most of the time, C is equal to D. But A and B are not equal because they are the diagonals. They are the diagonals. So in this case, what we can see is we need to find what are the formula for A, B, C, and D. Okay, so let's look at the formula sheet again. So we are interested at this four, and note that these are this symmetrical. This is the same as this one because it is symmetric. The matrix is symmetric, not the shape. So what we need to find. This is our A, this is our B, this is our C, and this is our D. Okay, so we can straight away use this. Okay, we can straight away use this formula. So in this case, my A is just B11 Y31 square plus B33 X13 square. Okay, note that what is Y31? Y13 is Y1 minus Y3. So Y31 is just the negative of Y13. Because if we change the sign here, if we put minus Y1 minus Y3, then it becomes Y3 minus Y1, right? So Y3 minus Y1 is just 0 because Y13 is 0. The negative of 0 is also a 0. So this is 0. How about D33? D33, I think we have calculated what is D33. Okay, so this is D33. 3.8462 times 10 to the power 9. Okay, times x13. X13 is minus 1, so it's just a switching sign. Just switching sign. So, sorry, x13 is minus 1. X13 is minus 1. Minus 1 square is just 1. So this is just 3.8462 times 10 to the power of 9. Okay, how about B then? B, if you take a look at the formula, is this. Okay, that's our B. So B is just B22 X13 square plus D33 Y13 square. Okay, note that Y13 is known to be 0. So any number times 0 is 0, and D22 is this number. Where is D22? Oh, D22 is this side. So this is D22, which is 10.989. Oh, okay. D22. Okay, D22 and D11 are the same number, are the same number. So we need to see what is the value here. So D22 is 10 point something, 10.989. Okay, so this is, if you do it correctly, 989 times 10 to the power of 9. Okay, so C, which is equal to D, is this formula. Okay, this formula here. So I do not want to write I do not want to calculate that. Just let me just write this formula. Okay, plus D3 x13 y31. Okay, and this should equal to 0 because y31 and 1y3 are 0. So this is 0. This is also 0, so this is 0. So now our key matrix for the first element is, as expected, it's a 2 by 2 matrix, right? It's a 2 by 2 matrix. And if you take a look here, if I remember this using global coordinate, okay, this is node 1 local, but if you look at our nodal connectivity table, this is our Q1, sorry, node 1, global node 1, global node 1, global node 2, and global node 3 based on our element connectivity table. So in this case, this is our Q1, not Q1, sorry. So this is our Q3 and our Q4 based on our nodal connectivity table. Q, small q is for local, which is element based. Capital Q is for our global base, global coordinate system. So now what we have is only Q3 and Q4. Q3 and Q4, because these are the only 2 degrees of freedom that we have for our element number 1. So for our element number 1, this is what we get, which is, if you do this correctly, then we have 10 to the power of 7, 3.8462, 0, 0, and 10.989. Okay? Okay, so what we have here, why is it 10 to the power of 7? This is 10 to the power of 9. Note that because of this, because of T over 4A in front of the formula, So now we are done with element number 1. So let's take a look at element number 2. So now element number 2 here. Okay, we redo everything. Element number 2. Okay, based on our nodal connectivity table. Okay, element number 2, local node number 1 is the same as global node number 3. So global node number 3 is this one. 2 and 4. So this is our node number 1, node number 2, node number 3 for element number 2. Okay, so this is node number 1, node number 2, and node number 3 of element number 2. Okay, it's frozen again. It's frozen again. And take a note that this is again counter clockwise. 1, 2, 3. 1, 2, 3. Counter clockwise direction. Counter clockwise direction. So we need to know the coordinates here. It's frozen. I cannot write anything now. Check if things eating up my memory. No, it's not eating up my memory. Something is not good with this PDF reader. So maybe I need to change the PDF reader to a better one. So let me end task. Yeah, Zafira. Any question?
Doktor, nak tanya yang C dengan D tu, how can it be equal? Saya tak faham tadi.
Okay, for element number 1, yeah?
Betul.
Okay, for element number 1, why is C and D equal? Okay, based on the formula sheet. Take a look at the formula sheet. Okay, let me kill this PDF reader. Okay, let me reshare this. I need to try to find a better one. Okay, so the question was, why is C and D the same? Okay, so let's take a look at the formula. Okay, I hope you have the formula sheet with you. This is from test 1 hari tu yang saya bagi ni. So take a look at this. Yeah. Why is C and D the same? Note that this one here. So this is my C, right? So 3, 4 and 4, 3 are the same. So these are the same. This is symmetrical. Can you see that this thing here? Okay, so that is the reason why C and D are the same. It's from the formula. It's given from the formula. So there's nothing new there. Nothing. All right, so this and this are the same. So take a look. This is my 3, 4, 3 and 4. This is 4 and 3. 1, 2, 3, 4 and 1, 2, 3. This is 4, 3. This is 3, 4. And from the formula sheet, it says that K34 equal to K43. Itu aja. Clear, Zafira?
Okay, clear now. Thank you, Doktor.
All right. So let's look at this one. Again, this is for element number 2. For element number 2, you can see that my numbering is 1, 2, 3 counterclockwise, and note that this is the one we had is for local. And if we look at the global coordinate, the global here, this is 3 to 4, 3 to 4. So 3 to 4 or 1 to 3. Okay, this is why this element connectivity table is very important. So let's continue that now. Let's continue this. So what I can do here is let me change the pen color. Let me use blue now. Okay, so this is our node number 3, node number 4, and sorry, node is not node number 2, right? This is, I think this is 2, 3, 2, 4, globally. Double check. Okay, 3, 2, 4, 3, 2, 4. Okay, betul 3 to 4. So now this is the global node number. The black one with the head is the local node number. So we need to do the same thing again. So what we need to know is what is the coordinate. The coordinate in this case x1. Let me use black. So this corresponds to the local. So x1 is given as 1, y1 equal to 1. Sorry, y1 equal to 0. X2 equal to 0.5 and y2 equal to -1, x3 equal to 1, and then y3 equal to minus 1. And again, what we need is x1, 3, x2, 3, y2, 3, and sorry, y1, 3, y1, 3, and y2, 3. So this is just the same thing as before. X1 minus x3 is 0. X2 minus x3 is minus 0 0.5. Y1 minus y3 is 1. Y2 minus y3 is 0. So we can get our J, which is just this number here, 0, 1 minus 0 0.5, 0 equal to, and of course this is the determinant of J is just minus half, and minus half A is half of the determinant of J, which is 0 0.25. And again, the formula for the matrix, stiffness matrix is the same. So T minus 4A, okay, this should be equal to 20 times 10 to the minus 3 over 4 times A. This is 1. So this is 20 to the, this is not, okay, this is to 20 times 10 to the 4 times 0 0.25 is 1. Hmm. Okay, so this is 10 to the minus 2. Am I correct? Something's, oh, sorry, this is 2. 2 times 10 to the minus 2. Okay, not 20, 2. Okay, so now, again, if you look at our element here, our second element here, we note that our Q1, Q2, this is equal to 0 and 0, right? Because at node number 3, here, this is 0 and 0. And if we look at element number 2 again, we know that this is Q5 equal to 0. Q6 is not equal to 0. And then we have Q3 and Q4. So note, we expect this to be a 1, 2, 3. A 3 by 3 matrix, a 3 by 3 matrix, because we know that there are 3 boundary conditions out of 6 degrees of freedom. So our K2 now is T over 4A, or in this case, 2 10 to the minus 2 times Q1, Q2, Q3, Q4, Q5, Q6. Okay, so we note that our Q1, Q2 is equal to 0 and 0, so we do not need Q1 and Q2. And because of that, we also do not need this one. Okay, how about Q5 and Q6? Okay, Q3 and Q4 are our unknown degrees of freedom. Q5 is 0, so we do not need this one. And at the same time, we do not need this one. So what we have here is now A, B, C. Oh, sorry. Again, I'm using this one. A, B, C. Okay. And then D and E and F and G and H and I. Okay, so note that because we have 3 degrees of freedom for element number 2, so our element stiffness matrix is also a 3 by 3 matrix. Okay, now back to the formula. and we know that we are interested to find, let me do this again. Let me delete all this because we do not need all this. Okay, so what we want to do is remember that our degrees of freedom, we are not going to use this and this because for element 2, these are zeros. So of course, these are not needed. We know 3 and 4 has no boundary condition. That is our unknown degrees of freedom. And Q5 is equal to 0. We are not going to use that formula. And of course, this corresponds to the same column. So what we need to do here is we need to find this, this, and this, and this, and this, and this one. Because the rest are symmetrical. Okay, so this will be symmetric with this one. Okay, 3, 6 is equal to 6, 3. Okay, this equal to this. So this is my A, my B, my C, my D, my D, E. So this is my D, this is my E, my F, and my G, my H, and my I. So you need to calculate only 1, 2, 3, 4, 5, 6 values instead of the whole thing, instead of 9. Instead of 9. So the rest are symmetry. The rest are symmetry. So again, I'm not going to show you all the calculation because I think you can do it on your own. So note again that this is our local degrees of freedom, but according to our global degrees of freedom, this is just equivalent to A5, Q6, Q3, Q4, Q7, and Q8. Okay, so this is the so this is the equivalent just now. So note that 5 and 6. Okay, for node number 1 of the local element number 2. So this is just mapping. Mapping. So okay. So this is, I think the procedure is simple, but keeping track is not as simple as you thought. So if you're not familiar with this, I suggest that you do this. Practice with this. Practice with this, because if not, then you might get confused and you might not be able to finish this during the test. So now if we use the formula again, we can get my A equal to 10.989 times 10 to the power of 9. B equal to 3.8462 times 10 to the power of 9. And C equal to, okay, note that our C has two terms. Our C has two terms. Not C. Okay, sorry. A, B, C has two terms. It's two terms, two terms, two terms, two terms. Everything is at least two terms. Okay, so C is again the same thing here. 6.5935 times 10 to the power of 9. And of course, now we can find that, okay, D and E, D equal to E equal to, D equal to E is just 0. Equal to 0 because of Y31 and 1Y3. These two are 0. So 0, DE, and then we can find F equal to G equal to 1.6484 times 10 to the power of 9, and then H equal to I, and this should equal to minus 3.8462 times 10 to the power of 9. Okay, by now, I think you can see that up to this point, we are doing number crunching. Kita calculate je, tekan je calculator, tekan je calculator. And keeping track which is the local node and which is the global node. Itu je, nothing else. Okay, so now comes the important part. So my K2, K2 is just 2 times to the power of 7 of all this number 10.989 0 1.6484 3.8462 minus 3.8462 and then 6.5935. Okay, so if I expand this, so this becomes 10 to the power of 7, and this is 21.978 3.2968 and 7.6924 minus 7.6924 and 13.187. Okay, so this is symmetric. This is symmetric punya matrix. So now we already have our element 1, which is this one, Q3, Q4. Okay, Q3, Q4. And now we have this for our second element. So I'm going to keep track of the global DOF, global DOF. No, it's not working again. So this is Q3, Q4, and Q8. Note that these 2 points, Q3 and Q4, are overlapping. Because we have Q3, Q4. This one is Q3 and Q4. And this one is also Q3, Q4, and Q8. Why do we need this? Because we need to assemble. We need to assemble. So what we have here is our reduced global stiffness matrix. Okay, so that's our capital K here. Okay, note for our capital. So 10 to the power of 7 is common for both element 1 and element 2. So what we have here is Q3, Q4, and Q8. Okay, so we need to assemble this. Why we need to see? Okay, Q3, we have Q3 and Q3. So this overlaps 3.84 and 21.984. So that's become 25.824. 824, sorry, this is 824. Okay, and of course, this is Q4, Q3, Q3 and Q4 is 0. Q3 and Q4 is 0. So this is 0. Q8, Q3. Is there such thing Q8 and Q3? No. That's none. There's none. So Q8 tak ada. So Q8 and Q3 is just 3.2968. Okay, of course, now Q3 and Q4 is 0. Q3 and Q4 is 0. So this is also 0. Okay, and then Q4 and Q4, 7.6924. Q4 and Q4, 10.989. So this one is overlapping. So we need to add them together, 10.989 plus with 76924, then this become 18.681. And then Q8 and Q4, Q8 and Q4 is not here. So this is exclusively for the second element. Okay, and if you repeat this, we should get this number. So anyway, this is symmetrical, and this is 13.187. And again, take note that our diagonal are positives. Our diagonal are positive numbers. Please double check this. If you get a negative number in the diagonal, then something is not right. Something is not right. So now this is what we get. This is what we get for our reduced stiffness matrix. Right, so we are almost done here. So what's the next thing to do? If you read the question, it asks for the, I think force, assemble the reduced global stiffness matrix for the whole structure. Done. Calculate the load at relevant nodes and assemble the global force vector. Ooh, how do we do this? So the next thing is our force vector. Our force vector. So our force vector is, so where is our force? So it's not working again. Where is our force? So if you look at the forces that we have, this is our element. It's not, again, it is, okay. So this is element 1, this is element 2. Is there any load at element number 1? None, right? So if you look at element number 2, we know that there's a uniform load, and at the same time, we also have our our concentrated load. So this is 2 kilonewton per meter square. Note that in the original structures, okay, in the original structure, hopefully I can open the file. This is assignment. No, this is not an assignment. This is just a discussion. Okay. Okay, note that in our original structure, the load is applied at this edge here, which is about 1 meter, about 1 meter kan? About 1 meter. So, but now, since we are only taking half of it, there's only half of the load here because the distance is from here to here, which is half the total distance from here to here. So note now, this is 2 kilonewton meter times, okay, times the distance, which is 0.5 meter, times the thickness, which is, in this case, 0.2 times 10 to the minus 3 meters. So meter and meter cancel out. So we have about 2 kilonewton of load. Okay? 2 kilonewton of load. Okay, from this point to this point. Okay, this is what we can see. Simple one. This is not from your finite element. This is just from maybe your static analysis. I cannot reopen my. Okay, never mind. Let's kill this. Let's kill this again. And we can reopen it later. Okay, now I kill it. So let's reopen. Okay, so let's reshare this. Let's reshare this so that you can see what I'm doing. Okay, right. So, okay, so this is the load, right? This is the load. And we also have this this concentrated load. And this is concentrated load of 10 kilonewton. Note that 10 kilonewton is for the whole structure. Betul tak? If you look at the original question, that 10 kilonewton is for the whole structure. It's for the whole structure. But in our case, okay, but in our case, we are only studying half of the structure, only half of the structure. Because of that, now instead of this equal to 10, it becomes only 5 kilonewton. So this is another important point. Yeah. So remember when we cut it into half, I say apply an appropriate boundary condition. So we use rollers, right? And now the loading becomes half of the original loading. Note that for the uniform loading, it's already half of the uh, load because we are only using this part here. We are not using the whole part. Okay, we are using half of the part here, so it's already half. But in this case, let's see that this node is shared between the left-hand side and the right-hand side. So in this case, we are only studying half. We are only using half of the load. Instead of 10, we are only using 5. This is another important point. This is another important point. All right, so now, can we find the force vector? Can we find the force vector here? Okay, so let's see how do we do this. Okay, I think in the formula sheet, there is a formula for uniform loading. For uniform loading. Okay, so let's see. Hopefully I can open this formula sheet. Oh, okay. So note that, oh, okay. There's no loading formula ke? Tak ada. Oh man, this is frustrating. Yeah, this one. This one. So these are the loadings. These are the loadings. Okay. This is the stress. This is the strain. Okay, these are just the shape function and so on. This is just the definition of x to 3, for example, y to 3, for example. And there are, this is for, note that this is for your body force, body force. But this is for your uniform loading, which is your traction force, traction force. Note that there are two formulas here. There are two formulas here and here. So which one are we going to use? This one or this one? Okay. So this one is also, I think, in my lecture, video. I hope you watch it. You have watched it, and I hope you know which one is. But in this case, I'm not telling you why, but I'm going to use this formula. I hope you know why I'm using this. Okay, so I'll be using this formula, this one. So my load here, my load will be, okay, my load for this element, my uniform load, my uniform load will be TL over 2 times dx dy dx dy. Note that this is equivalent to our F3, F4, F7, F8, because if you look at this, this is 1, 2, 3, 4. And the load are at F7, F8, and F3 and F4. There's no load at F5 and X6, F5 and X6. So there are only that. And furthermore, note that there's no load in the X direction for F3. Tak ada, X direction tak ada. X direction at node number 4 is also not there. It's just only vertical load. So in this case, when I substitute this value, so my T is equal to TL over 2, my thickness is 10 times 20 times to the minus of 3 times my L, length is 0.5 meters, divided by 2, and note that in the X direction, there's no such thing, there's no such load, and Ty is minus 200, 0 and minus 200. Why is it minus 200? Because it is going downward. It is going downward. Note that the total force here, is 2 kilonewton per meter square time 0.5 meter time 20 times 10 to the minus 3 millimeter thickness. And this is cancel out. 2 kali 5 is 10 kali 2 is 20 kilo Newton, right? Sorry. Can anybody calculate that for me? For berapa tu? Half is 120. Oh, okay. Sorry. Betul lah, betul. So this part here is already calculated, but our T here is our T here should be okay. This should be the total should be this number 0 minus 10 0 minus 10 kilonewton due to distributed load. Okay, so this is my thickness, this is my length. Okay, my length. And if you look at this, uniform loading, okay, total loading here is 20, it's not 20, it's 2 kilonewton. Newton per meter square times length 0.5 meter times thickness 20 times 10 to the minus 3, and this should be equal to, the total load should be equal to 20 kilonewton 20 kilonewton is it 20 kilonewton or 2 kilonewton? 2 kilonewton, sorry, 2 kilonewton, or 2000 newton. Total, 2000 newton. But note that because half of it will go to this node and the other half of it will go to this node. This is why we get 10 and 10. 10 and 10. Okay, that is why we get 10 and 10. Okay, so in this case, this is just 2 kilonewton. This is the load. This is the load, 2 kilonewton and 2 kilonewton. What's the formula? Okay, this is the one. T downward is T Ty. In this case, Ty is equal to 2 kilonewton per meter square. Okay, so that is the value. Minus 2000, minus 2000. Note that this is going downward and then it's a negative number because of the direction. So I just plug in this value and half of it, half of the 20 kilonewton, half of the 2 kilonewton will go to this node and another half will go to this node. And the total is minus 2 kilonewton, which is correct. So this is my T at element number 2. For L node, I don't remember what node is that. Node 2 and 4. Node 2 and 4. This one. So that is the distributed load. That is the distributed load. And note that again, this is 3, 4, 7, 8. And note that our 7, our degrees of freedom for 7 is 0. So our T is just 0 minus 10 and minus 10. Now, let's look at our one more node, this one. This one. So force vector, and now this is due to point load. Due to point load, we note that our P is just at node 7, 7 going downward. So note that we are only inserted at this node, which is 3, 4, 8. 7 is has the boundary condition of 0. So this is 0, 0 minus 5 kilonewton or 5,000. 5 kilonewton, which is minus 5,000. Okay, so this is due to point load. So total force vector, okay, global, total global force vector become 0 minus 10 minus 10 plus 0, 0 minus 5,000, and it becomes F equal to 0 minus 10 minus 5010. So note that this is from the uniform load. This is from the point load. So now we can basically find our global displacement. So of course, this is our global K matrix. This is our degrees of freedom, Q3, Q4, and Q8, and equal our force vector, which is 0, minus 10, and minus 50, 10. And of course, you can solve for Q3, Q4, and Q8. Okay, this is from using your calculator. So what I get here is 6.6 times 6.6687. 6.6687 times 10 to the minus 6 meter, micrometer, minus 2.15 63 times 10 to the minus 5 meter. And then this is minus 5.2238 times 10 to the minus 10 to the minus 5 meter. Okay, so take a look at the shape now. If you look at the shape now, okay, so once you get this, you can calculate all the other related values. So saya tak nak buat lah. I think you can do it on your own because I think we are out of time actually. We are out of time. But so hopefully you can still stay for a while because I need to show you the shape. The shape. So the shape of the structure after loading. So let's say this is before loading. And this is our Q1, Q2, Q5, Q6, and this is our Q3 and Q4. So Q3 move positively. Q3 move positively, which means after the loading, this is what happened. Okay, this is what happened. Q3 move to the right hand side, but Q4 is going downwards. So this is what happened. So this become this because from this point to this point a positive, but from this point to this point is a negative. And Q8 is basically originally Q8 is here, so it moved to maybe this point here. So this is the deformed shape. This is the deformed shape. This is the deformed shape. So let me delete this. So let me redraw this nicely. So this is the original Q5. Sorry, 1, 1, 2. This is Q3 and Q4. So Q3 move to the right hand side. So this side, but Q4 is going downward, negative. Yeah. So this is the shape. This is the shape as we predicted before. So this is the solution. So please take note. Try to redo this on your own. Hopefully you get the same answer as mine. And then once you get this, you can continue with the rest of the question. Okay, I think that's it for today's session. Okay, that's it for now. Thank you, everyone. So we see you again on Sunday. On Sunday. All right. Thank you, everyone.
Thank you, Doctor.